chapter 3, especially today, we're going to talk about extrema. What do you think of when you see that word extrema?
Extreme.
Extreme. Now in math, extreme means really high or really low, okay? So we're going to be talking about maximums and minimums. Okay, extrema, by the way, is plural. Extremum is singular, which seems weird, but it's from the Greek, okay? So it says we're going to define it. Let f be defined on an interval I containing c. Now, do you think c is an x value or a y value? If it's on an interval, what are intervals of? X or y? If I said something is happening over the interval 0, 2, it would be for those x values. So c is an x value. Oh, that's really close. All right. And that's important for this reason. F of c being the minimum or the maximum, okay, I'll explain the rest of that. These things are y values. So when I ask what is the minimum, what is the maximum, I'm saying what is the y value, all right? And that should make sense. If you're saying really high, the y value is what makes it really high or really low. Okay, so f of c is the minimum of f on this interval if that y value is less than or equal to f of x, meaning if that y value is the lowest of all the y values, it's the minimum. Does that make sense? If the y value is the smallest, minimum. If the y value is the largest, maximum. You can have a tie. So like moving on to part A, find the absolute, well, I don't want to skip over this part. The minimum and maximum of a function on an interval of the extreme values or extrema, they are also called the absolute minimum and absolute maximum, okay? So let me just say, next page, we're going to deal with relative minimum and maximum, and I'll explain the difference. But so if there's no word in front, absolute is implied, and that just means the absolute highest or lowest. Okay, so find the absolute extrema. Well, right down here would be the absolute minimum. Now remember I said I'm really concerned about the y value. So you could give the coordinates 0, 1, but it's much better to write it as f of 0 equals 1. All right, because f of 0 is like that f of c, and 1 is the minimum y value. It is the smallest y value of all the y values. So do you see the max? How would you write the max? F of 2, 2 would be the c value, equals 5. So if I said, what is the max? You would say 5. If I said, at what x value do we have a max? It's 2. So notice that the minimum occurred at like kind of a curve in the graph. The maximum occurred at an endpoint. It could be either way, all right? Look at how B, though, changes this, okay? The minimum is the same. That hasn't changed. It's the exact same as A. But look at right there. What's happening at where the max was? It's a hole. You cannot have a max at a hole. Now, we can get into a whole conversation as to, well, the max would be then like 4.99999, or you could use limit, but we're just going to say that that point is not a max. We're going to leave it at that. We're not going to talk about what the max would be, or even if it exists. Right. If you have a hole, then you don't have a point, and it can't actually be a max or a min. Okay, so then on C, the max is still good, but what happened with the minimum? Yeah, that point right there is not a minimum. Now, there's a hole, and there is a point that's not at the hole. Okay, and we even have discontinuity here. So this kind of boils this all down. A function need not have a minimum or maximum. There really should be a comma right there. So this just means there doesn't have to have a minimum or maximum. I'm going to give you some qualifications pretty soon where we will for sure have one, but just your standard function may not have one, okay? Also, what if there were arrows that kept going up? Then you wouldn't have a max either. All right? And so that's number one. Number two, continuity can affect. So see here on C, we have a discontinuity. That affected the minimum. What if the discontinuity had occurred like over here? Would that affect the max or min? No.
No.
All right. So here's what we need. If I'm going to say for sure we have a max and a min, this is what I need. I need continuity. Now, what is for sure not going to be there if you have continuity? A hole. What else? A vertical asymptote. Those are the main things. Okay? We also need endpoints. See on choice B how we didn't have an endpoint, and you could say, well, that's a hole. You're right, but we don't have an endpoint. It doesn't actually stop. It just has like a stopping boundary. All right, so we need endpoints. Those are the two things we need. All right, so then we get into this idea of the extreme value theorem. Now, have you ever heard of a theorem that would named kind of like this, but like instead of extreme, there was another word? The blank value theorem. Intermediate value theorem. You have a theorem card on this, that purple theorem write-up. Hopefully you still have that. Okay? So, extreme value theorem is kind of like intermediate. Remember, intermediate was saying if we have 2 points and we know the y value is in between the two y values, then the x value also has to be in there, meaning in the middle somewhere in between. Extreme value has to do with the extremes, the max or min. So look at what the conditions have to be. F has to be continuous. So this is what we said right here. We need continuity. All right? We also need a closed interval. That's what having endpoints does. If you have endpoints, you have a closed. Remember the difference between bracket and parenthesis? It meant that you either have the endpoint or it's like a boundary. Okay? If both of those things occur, then F has both a minimum and a maximum, and these are absolute minimums and maximums. Okay? So, this you're going to do a theorem write-up over tomorrow. So we're going to use it, but I want you to be thinking about what this is, and remember on your theorem write-up, you got to write the theorem. It's right here. You got to explain it in your own words. I've kind of helped you out with that. You've got to draw a picture. We have some pictures up here. And then you've also got to put an example. So all of that's on your notes, but you're going to have to put it on the theorem write-up card tomorrow. All right, before we move on, let's review continuity. Okay, because continuity has to be where we begin. If a function's not continuous, then I can't even use extreme value theorem. So there were, if I'm thinking of the definition of continuity, there were 3 things to that theorem. And this, again, you have a theorem write-up on definition of continuity. I had you guys do these cards for a reason so that you could have them to go back and look at. And by the way, the back of your after party due tomorrow, you have to be using these things. You have to use the definition of continuity. It says in the directions, it's like the very last 3 problems, use the definition of continuity. So you need to be using these things. So does anybody remember what the first one was? And the hint is it has to do with limit. The limit must exist. So the way, I'm going to go ahead and write out the whole thing. The left-sided limit at any particular C has to equal the right-sided limit at that same number. Which another way of saying that is saying that the limit as x approaches C exists. So the limit has to exist. What else has to exist? The point, the actual point. It can't be that just the limit exists. Look right up here. We have a limit around that hole, okay? But the point has to exist. And hey, the point even exists up here. So what's the deal? What's the third thing? They have to equal each other. So the limit as x approaches C of f of x has to equal f of C. So that was just a quick review of continuity. So we're reviewing a lot of stuff from chapter 1 right now. It's gonna look a lot like that, and it's gonna use a lot of the derivatives from chapter 2. Okay, so let's look at the next page. So that was absolute. Now we're gonna talk about relative. Now, when you see relative, there's another word you need to think of, and that's local. Both of those imply a very small area. Okay? Like, think of it this way. I was telling another class. I have 3 best friends. They're all pretty short. Okay? They're all like 5'1", 5'2". I'm not saying that's bad, but I'm not like that. So when I stand next to those 3 people, I appear to be really tall. Even some of our other friends are like, you look so tall compared to these other 3. And the 4 of us are like really good friends. We take a lot of pictures together, and I'm always like hunched over. Okay, because relative to them, I am very tall. But if I go and I'm just like in a group of people, and let's just say some of those people are like professional basketball players, am I tall? No, and I'm definitely not the tallest person in the world. That would be an absolute, okay? Relative, I'm relatively tall compared to those 3 short friends. That's what you need to think. You can zoom in on just a little area. That's what a relative max or min, and sometimes they're called local. So if we have an open interval, which means that not the whole thing, but you just zoom in on one little piece. If we have a maximum, that's a relative max. So, and same thing with the min. So let me kind of explain it to you in this picture. So let's pretend for a minute that we have endpoints. We're going to change these to arrows in a minute. But right now, do you see the absolute max and min? I'm switching back to absolute here. So the absolute max would be over here on the right, the absolute min would be over here on the left, and all the points are in the middle. All right, now let me change these to arrows because that's really what this graph is. Now where is the absolute max or min? The absolute max or min doesn't exist because the graph continues up. But, and some of you are already thinking this way, the relative maxes and mins are these little tiny isolated cases of if you zoomed in just that section, it looks like a min or a max. The thing with relative extrema, like for instance, relative min, typically the way the directions are, you're not usually asked what is the relative min, you're asking where or when or at what x value is the relative min. Okay, so with absolute, mostly we're concerned with the y, although it depends on the directions. With relative min, we're mostly concerned with the x. So that right there would be the relative min. All right, and so what would you say is the x value right here? Is it at 2 or -4? 2. Okay, so that's the way this is listed out. Now, I do want to practice function notation a little bit more. So you could say f of 2 equals -4. But if the directions specifically ask for the x value, all you would have to give is 2. Okay, what about the relative max? Where is that happening at x equals what? 0. And if I box that, and then if I wrote this in function notation, what would I write? F of 0 equals 0. F of the x value equals the y value. Okay, so that's what a relative max or min is. So when we look at these examples, you may see some of these and think, well, they're both. It's a relative max and an absolute max. And you're right, a lot of times they are. It just depends on the picture. All right, so we're going to kind of go through a little thing, and I'm going to see if you can tell me in a minute what goes in these 2 blanks. So it says, find the value of the derivative at the indicated relative extrema. So in other words, what is the derivative right there? We could go through the laborious process of finding the derivative by hand and then plugging in 3 and computing. Or we could use common sense and say, I'm so glad they gave me a graph. What is the slope at that point? You can draw a tangent line just to really make it clear. What's the slope right there? 0, right? That's the derivative. In other words, that's what f prime of 3 equals. Remember, f of 3 would be the y value. F prime of 3 would be the slope. It's all the same stuff we've been talking about. It's just, I'm going to keep throwing it at you different ways so that you really get it. All right, so do you think that every time we have a max, the slope will be 0? Let me go up here just a minute. What's the slope up here at our max? So at a relative max, do you think the slope is always 0? It is here, and at the relative min it is. Let's see. Let's see if B is going to throw a kink into things. Look at B. This is absolute value. You knew what this graph looked like, which is good because you don't even know how to take the derivative of that by hand.
Oh, yes.
What is the derivative or the slope at that? Why does it not exist? There's a cusp there. When the graph sharply turns, like a corner, not a smooth curve, but a sharp turn, a cusp, we don't have a derivative. So you can say does not exist, or you can say undefined there. All right? And so this is the special scenario. Most of the time, we're going to get 0, but we do occasionally get does not exist. Look at C. Here's a trig one. What's the slope at this max? 0. What's the slope at the min? 0. And if this continued, we'd keep getting those. So like on sine and cosine, you have lots of maxes and mins. So what should go in these blanks down here? At relative extremum, the derivative is either what or what? 0 or, we could say or does not exist. I'm going to go ahead and say undefined here. All right, and so relative extremum, f prime, 0 undefined. Okay, turn the page. Now I'm going to throw another phrase at you, critical number. Now you've probably heard your math teacher use this phrase, mostly when like graphing trig. Remember how you had to write all the tick marks out? You had to divide the period by 4. You might have called those critical points. And that wasn't it. That was a good use of that phrase, and it has everything to do with this. But when we say critical number in here, this is what we mean. We mean f prime equals 0 or f undefined at C. All right, that's what a critical number is. So now we have another theorem. See how this theorem is just theorem 3.2? It doesn't have a special name. We won't do a theorem right after this. It's still important though. It kind of combines what we just said. Relative or local extrema occur only at critical numbers. So we have 3 concepts that go hand in hand. Critical numbers, relative extremum, and the fact that the derivative is 0 or undefined. All 3 of those bounce back and forth to each other. Okay? It's like the holy trinity of this section 3.1. Okay? Now, on the other hand, absolute extrema, they can occur at critical numbers. Because remember, a relative max could be the absolute max, but they also could occur at endpoints. So I'm kind of coming full circle with this lesson. All right, it's really testing if you really understand these phrases. So let me go back to the first page, and I'll come back to this. All right, with this absolute min, was that also a relative min? Yes. So this right here, 0, is a critical number. All right? Right here, this absolute max, was this also a relative max? If you zoomed in right there, would you see the graph go up and then down again? No. But this is an endpoint. Okay, so relative, I can put it like right here, relative and absolute, both of these that would be fine. Over here, this is not a relative max. This is an absolute max. So that's why we have to say that. So here, right here, put stars around this, highlight it, do what you want. These are the steps to finding absolute extrema, and this is what we're going to spend the rest of the lesson on. Okay? And this is more like math. We're going to do derivatives and plug in numbers and all that. Okay? So if we have continuity, remember we had to have continuity to do any of this. We also have to have a closed interval. It can't just be some function forever. It has to be closed interval. So before I even look at the others, look at my answer choices. We have continuity and we have a closed interval every single time. So just noticing that. Okay, number 1, find the critical numbers. Remember, critical numbers, if you need to write this off to the side here, are when f prime equals 0 or is undefined. Once we find those critical numbers, then we're going to evaluate them back into f. In other words, we're going to have all these x values that we're going to test. Okay? So looking at A, locate the absolute extrema. What we're going to do first is find the derivative. And you are experts at this by now, hopefully. 12x cubed minus 12x squared. And we need to check for two things. When f prime equals 0 or is undefined. I find that students forget this one. So let's do this one first. Where is this thing undefined? This derivative. Do we need to review how to do that? What y'all think? It's not. Yes. Right, so just kind of off to the side. Undefined would be when you get a number over 0 or when you square root a negative. So could either of those happen here? No. You're not going to get 0 in the denominator because there is no denominator and there's certainly not a square root. So this thing is not undefined. So we could say there's no critical points. But it's something you have to check. Like in this example, we're going to have that we are going to get a number out of that. Okay, next thing is we're going to set f prime of x equal to 0. Okay, so set 12x cubed minus 12x squared equal to 0. So I want you to solve this. My hint is factor. So without a calculator, solve for x. Whoops. What did you guys factor out? 12x squared, and so what are you getting for your x's? 0 and 1. Good thing too, because those tend to be easy numbers to plug in. Okay, these are your critical numbers. In other words, I possibly have a relative max or min at x equals 0 and x equals 1. Probably one of them's a max and one of them is a min, although I don't know that for sure, unless I do more of the problem. So if they're possibly relative maxes or mins, then they're definitely a possibility for absolute. Okay? The other possibilities are the endpoints. So we're going to take both of these things, 0, 1, negative 1, and 2, and what we're going to do is we're going to plug it in, and I'm going to make the tiniest table that ever existed. 0, 1, negative 1, and 2. I'm going to take these numbers and I'm going to plug it back into the original because I want to know what are the y values that correspond to these x values. By extreme value theorem, one of these is the biggest, absolute max, one of these is going to be the lowest. And I could have a tie, but the only way to do this is just crunch the numbers. And so in other words, first we're going to find f of 0. Okay, so plugging 0 in, 3 times 0 to the 4th minus 4 times 0 cubed. What does that turn out to be? 0. Right? As much work as you need for this, by the way. Write it all out if you need to. Or if you can do it in your head, that's great too. But this is something you should definitely be able to do without a calculator. Alright, what about f of 1? If you plugged in 1, 3 times 1 to the 4th minus 4 times 1 cubed. Yeah, don't plug it into the derivative, and if it helps you, maybe even like lightly cross it off or something. We use the derivative to find the x values, but we have to go back to the original because we're looking for y's. So what's f of 1? Negative 1, because it ends up being 3 minus 4. Okay, what about f of negative 1? 7. You're like, how'd they get 7? Go off to the side, plug in negative 1, crunch the numbers, you'll get 7. All right, what about 2? What's f of 2? This one's a little bit harder. Maybe you can't do this in your head all the way. Maybe you need to write down some steps. It is 16. Okay. So do you see which one is our min? Our absolute min is negative 1. Remember the absolute? Really, if you're just saying what is the absolute min, it's what's the y value. If by chance the direction said, for what x value do you get the absolute min? Well, then you would give me the x value, but that's not really how that question is going to be asked. All right, what about the absolute max? 16. All right, and that's how you do these problems. The hardest part here is sometimes the derivative is hard, but crunching all the numbers, that tends to throw students. The worst thing you can do for yourself is when you're practicing this is use your calculator. Because then you're going to get used to it, and then I'm going to give you a quiz, and you're going to go, whoop, I haven't been crunching any numbers the last week, and my brain totally forgot how to do it. So try it just using, your brain, and then if you want to check in the calculator, you can. All right, so let's try another one. So do you remember what the first step was? Take the derivative. Okay, so let's do that. F prime of x equals.
Wait, do we have to find what there's might be a relative?
No, not for what the directions. See how the directions were locate the absolute extrema? We're going to get to how do you know for sure you have a relative max or min? I didn't say this yet, but we're going to do that actually next week. It's a little bit more involved. This is actually easier. I don't know. Some people think the relative is easier. It's just more like logic. This is more just crunching numbers. All right, so f prime of x. We got 2. What do we got next? Minus what? What's 2/3 times 3? 2. What would be the new power on?
I got it right.
Yeah, you might have rewritten it. Now, here's the deal. This is totally fine if that's all we're doing. But I'm about to have to set this equal to 0 and do all sorts of stuff. It is going to be more beneficial for you to really know what this says. So let's rewrite this. Okay, watch what I'm going to do here. This has been throwing people off all day. Okay, x to the negative 1/3. The negative means, hey, put this x in the denominator. What is the 1/3? It means to cube root it. Okay? So remember, we have to check 2 things. We have to check undefined and 0. So where is this thing undefined at? This is undefined. Where at? What x value?
Because 0.
Yeah, what x is going to really throw a wrench in this machine? 0. And if you rewrite it, it's a lot more obvious. Okay? The cubed root part is no big deal because you can cube root a negative all day long. You just can't divide by 0. All right, so that's one of our critical numbers. All right, let's find the other ones. That's going to be where we set our derivative equal to 0. Now, this has also been throwing people off. It's all the algebra. Okay, so I'm going to encourage you just to watch me work through this algebra, remind you of some things, and then I'll give you time to write it down. So the way I look at this is I want to move this over to the other side. I want to add it. Sorry. Let me do that. All right, so we want to say equals 2 over the cubed root of x. The second thing is I don't want a fraction if I don't have to have it. So I'm going to put that 2 over 1, and I'm going to cross multiply. So I'm going to get 2 cubed root of x equals 2. Now what do you think we could do? Divide by 2. And you get cubed root of x equals 1. Cube both sides, and x equals 1. So my critical numbers, just to rewrite it, is x equals 0, because remember, we got that from right there, undefined, we did that one first. And then we got x equals 1 when we set the derivative equal to 0. So that was a little bit more work than the last one.
Why is it that setting the derivative equal to 0 gives you the critical points?
Because remember, the derivative is the slope of the tangent line.
Right.
So if the tangent line is horizontal, meaning
Oh, it would
slope
be
is 0,
zero.
then it represents the graph going up and coming back down, like
Okay.
a little max or min.
Then-
And that's what you're finding here. Like this x equals 1, that's a probably going to be a relative max or min.
Okay.
We'd have to do more to determine that. It's a good question. Great question.
I was thinking it was just like factoring. So
Yeah. Okay, so now we got to set up a table. Got a meeting. Okay. Now we're going to set up a table. Now what numbers do you need to plug in this table into the x column? Your critical numbers. You notice how that's 0 and 1 again? I'm trying to be easy on you, at least a little bit. Those are easy numbers to plug in. And then also your endpoints. One of these is going to be worse than the other. Okay, I want you to take one of these and figure it out. You can try to do the one you think is the easiest, or try to do the one you think is the hardest. But everybody take one of these and evaluate it.
Why is 0 1 of them?
Because f prime was undefined at x equals 0. Remember, critical points are where f prime is undefined or where x equals 0. Everybody always forgets the undefined one. Yeah. So you're just looking for one of them. And remember, you plug it in to the original. Who chose 0? Y'all are either lazy or smart, or maybe a combination. What was f of 0? 0. Okay, anybody choose 1? So what's 1? Negative 1. Because it ends up being 2 minus 3, right? Because 1 to any power. What about negative 1?
Negative 3. No?
It's going to be negative 1.
Let me get them down here. So 2 times negative 1 minus 3 times negative 1 to the 2/3. Look, negative 1 to the 2. Look, 2 is still square. What happens when you square negative 1? So what is that?
Yeah, negative 2 minus what? Negative 5.
Negative 5. So the number crunching on that one was a little weird. It's really weird on the next one. Okay, so let's do this one together. So you plug in 3, you get 2 times 3. Okay, that's 6. That wasn't too bad. Minus 3 times. Okay, x to the 2/3. That is the same thing as the cubed root of x squared, and so it's 3 squared, which is 9. So I just plug 3 in, and I get this, which is not a whole number. You can still, first of all, determine if it's your answer. But let me just tell you, typically, the weird one, like 95% of the time, the weird one is not your answer. Don't ever think that that's your answer. It's not, okay? It might be like once in the blue moon, but it's not really going to be your answer. So what we need to decide is if it's lower than -5 or higher than 0. That's all we need to know, because if I can rule those out, then it's not my answer, okay? So watch this. What's cubed root of 8? 2. Everybody knows that, right? Cubed root of 8 is 2. So cubed root of 9 is like just barely more than 2. So watch this. 6 minus 3 times 2.1. I'm just estimating here. What number is that really close to, first of all?
Negative and well, 0.
It's very close to 0, but it does have to be negative, because 3 times 2.1 is going to be like a bigger than 6, negative number. All right. Long story short, it's not our answer, and I told y'all, if you're stuck, don't pick that one. Pick the other ones. Okay, so what is our absolute min? Be careful with that. What's the lowest number? The lowest number on the graph. -5. And that's easy to do. I even do that sometimes. Absolute max then would be 0. This is all stuff you should be able to do without a calculator. The reason is because if you had a calculator, how would you, maybe like last year or the year before, find the max or min? Graph it and do the max min function. Super easy, right? You can use that to check your work if you'd like. All right, I'm not really going to do that because I really want you guys to get good at this. We're not going to do this problem. You are more than welcome to do this one on your own. But let me tell you, you actually know the answer without even doing the work. How do you know that?
Because it's pair function.
Yeah, sign goes up to 1 and down to -1. So, you know, this would be okay to do it this way if this was multiple choice. If it was free response, you'd have to show your work. We'll get to that another day. But if you already know the answer, at least you know when you're right or wrong. Okay? So some of these you know.